I want to talk a little. Anyway, it's running. Okay, round two after almost destroying my camera. Want to be a part of our video? All right, guys.
No, are we on?
Yeah, we've been on.
Oh. Alright, well this is our fancy dancy tracking, camera tracking system right here. Track
I believe the name was video-based object tracking.
This is a video-based object tracking system. So basically what we have is just like a standard Panasonic, camera on a pan and tilt module, which just allows it to go up and down, left and right, and then there's a laser here on the contact motion system that points at objects as we find them. So, data flow control wise, what we have is, so we have analog video coming off the camera, and it's coming into the input port here, which is fed into the ADV7180, which Tim can tell you about.
So the ADV7180 is a video decoder chip that's on the dev board, and it's configured over export C, and then it takes analog video and converts it, or digitizes it, and spits that out on an 8-bit parallel beta bus. And we took that signal and ran it through a resized module that takes the YUV color space image data, and it's going to resize it from full VGA resolution to QQ-VGA. So we're at 160 by 120 pixels. And we do that by averaging the pixels together, so it's a little bit more complicated. And then that video is stored in a frame buffer, which is in block memory on the FPGA, and that block memory is connected to the external memory interface of the ARM.
And so basically, we have basically a set of external memory sitting on the FPGA, and then what we can do is there's a separate, it's called the EMMA, which is Enhanced Multimedia Accelerator on the ARM chip, which is actually separate than the ARM. What that allows us to do is you can set up a bunch of configuration registers, like where your source address is, where your destination you want that to be, and then you tell it like how many pixels wide, how many pixels tall, and if you want resizing and a couple other things. Those are all just memory mapped registers, so you write values. And then there's a control register for the EMMA. So you set one bit in the control register, which enables the conversion. So once you enable a conversion, what that does is EMMA will go get data off from the source as it needs it. So in this case, it's getting data from the FPGA. And it'll bring it in byte by byte, run the floating point calculations on it to convert that YUV to RGB, something that we can actually understand color-wise, and then it will send that to the source or the destination address. And so by that point, we actually have data off the FPGA and now sitting in SD-RAM where the ARM can access it much faster, and it's also in RGB, so it's in the correct format for our image processing algorithm.
Cool.
Want to talk about your... You want me to hold?
Don't drop the camera this time, Tim. Well, actually, it was me who dropped it.
I helped.
Anyway, so the blob detection, all that, or how the actual video processing does, once it's in the external RAM, or in the RAM in the FPGA, that's stored as just each pixel is an individual byte, and for every 2 bits that represents red, green, and blue, so you know it's actually only 7 bits of data. And then to simplify things in software, we just converted each color to a letter. So like you may have red, maybe A in the software. So that made thinking about it and processing it really easy. So once we pull in that buffer, we go ahead and search for a particular color to find a blob. So we find all the pixels that match the color we're searching for. And then we basically create an artificial square around that blob. And then we put 2 diagonal lines around the square at the edges, and we find the intersection of those lines to find the center of the blob. So once we find the center of the blob, we can go ahead and tell the pan and tilt module to constantly try to center the blob into the middle of the picture. And that's basically how the blob detection works. And it's really easy to switch between colors. It also works really well because we only collect 64 colors. So it means like reds are going to be matched under the same letter as we just described. So we don't have to worry as much about different shades of red or different shades of other colors. more simple too, and it works pretty well, as you'll soon see.
Oh yeah, just a note on servos. So basically in software we just write to a memory map address a value 0 through 1024, and then so there's a Verilog module that monitors those couple addresses, and all it does is it calculates the what fraction of 1024 that is, and then converts that to an output pulse. Basically servos are just like pulse width modulated. You send them a signal or a signal that's high for a single amount of time. So basically what we do is we take the 66 megahertz clock off the ARM, use a clock divider to bring it down to a 1 megahertz clock, and then we literally count clock cycles that were high, and then once we get to we're high, the right amount of clock cycles, we pull the line back down, and you have to do that every 20 milliseconds for a servo. So it is, let me give you a, right now we're in manual mode. Can you see the screen pretty well?
Yeah, kind of.
Okay, so this is manual mode. We have, Chris made us a nice full console here, so you can press, use ASDW to move the camera around manually, which is kind of nice. Ooh.
Oh, it also has the feature that if you, oh, never mind.
Oh yeah, here. What is it? J makes a score? F.
F. So yeah, if you press the space key, it will shine the laser,
Which is on my hand.
and then you can also make squares for kicks. So,
Here.
but your hand isn't big enough. Oh yeah, it is.
Square. So it makes a little square on my hand.
Yeah.
And then spacebar turns the laser back off. Another thing you can do in manual mode is you can basically color sample something. So if I hold up an image in front of the camera, it will see that image, and then what it does is it takes the middle third of the image each way and literally just counts pixels. So it counted those and it sees what occurs most often. It'll set that as the custom color. Let's try taking it a little bit further. I don't remember what blue was before. Plus. Let's try this one. Try a different color. Things change under different light settings, which is good and bad. Oh, did we turn the camera off?
No.
Did we change the light, the balancing?
We're at 7 minutes. You get.
Okay. Okay, so then we'll exit out of this, and then, so basically, right now it is in search mode, and by default it searches for red, so to see something red...
Oh, did you actually?
I think it's in red.
Yeah.
Red.
So another quick note is that not only can you color sample, there's also preset colors. So at the command line, you can also type red or green or blue, and then it'll automatically start searching for the color that you say. Let's also enable the laser to demo it once it's working.
Try green. So now it's locked in,
Alright.
Did we change the camera settings?
They were still there.
Huh.
We can edit this out. Yeah. Now I'm checking that. Yeah, there we go.
Yeah.
That's better.
Alright.
Good
So,
job, buddy.
well, let's go ahead and enable the laser. So there's a command to enable and disable the laser so you don't blind yourself. And you'll see that it goes ahead and is pretty accurate. Go ahead and move around the thing.
Yeah, let's go down so it doesn't blind me. For camera. I'll go up and down too. Okay, I'm gonna change. Try different colors. Green. There. Okay. Oh no.
Liking the wall.
Okay, so now it does see that as 9. Just exit out of there and go custom. Okay. Green. Don't ask me why, but I feel like custom works better for some reason, because green is still 9. That doesn't make any sense. But see, it's tracking pretty well. Doesn't need to track up and down fairly smoothly. Oops, weird. You can do like little things like I can make the camera do circles. You can make little squares. And this track's decently fast.
And then you'll see that once you take the color away, it automatically goes into search and destroy mode, or just automatically starts searching the area trying to find the color again.
Do you have any other cool features?
Yeah, let's take a picture of me with the camera.
Let's go into manual mode. So in manual you can, oops, wrong way. Come up closer, it'll probably want you closer to,
Down.
oh, oop, that's up. See, decently centered?
There we go. Yep.
Good?
Yep.
So we can take a pic, and zoom in on the, can you see that decently well on there? Yeah. Okay, so that's like what? That's
And there's me holding the
Chris's
camera.
face, there's
This is his
Chris,
body,
his
there's his
hand,
hand.
and the camera is right there.
Up there.
Maps the same color as your shirt.
Mhm. Which makes sense, black and black.
And there's my hand right there waving to you guys.
Yep.
Yep. So, yeah. Do we have anything else we want to say?
Not that I'm aware of.
So, this is our super awesome award-winning project.
Award-winning, I make it sound bad.
Yeah.
So, yeah. Any final comments?
No.
All right. Goodbye, peoples.